Welcome to Module 1, an introduction to linear algebra. This is Lesson 1, where we will explore the fundamentals of linear algebra, why it is so important, and how it powers countless real-world applications in data science, machine learning, and artificial intelligence. Linear algebra is one of the most foundational branches of mathematics. It provides the tools to solve linear equations, analyze linear transformations, and work with vectors and matrices to model, manipulate, and gain insights from data. But why is this so important? Think about any modern technology. Linear algebra is at the core of it. It powers dimensionality reduction techniques like PCA, drives the calculations behind neural networks, enables recommendation systems, data compression, feature engineering, and clustering algorithms. And these are just a few examples. There are many more applications that make linear algebra indispensable in today's data-driven world. It is a mathematical foundation that enables us to manipulate, analyze, and truly understand the data that shapes our technology and decisions. So, what exactly is linear algebra? At its core, it is the study of linear equations, functions, and their representations. For example, consider the equation y equals ax plus b. This simple relationship describes a straight line pattern in two dimensions. Now, scale this up to multidimensional spaces and you have vectors and matrices, powerful tools that allow us to represent, transform, and extract insights from data. As we mentioned earlier, linear algebra isn't just about theory. It is deeply practical. From the long list of applications we mentioned, let's explore three major ones: principal component analysis, or PCA, image transformations using matrices, and the role of linear algebra in neural networks. First, let's discuss PCA, a technique used to simplify complex data sets. Imagine you are working with data in three dimensions. Think of it as clusters of points in space. PCA reduces these three dimensions to two, preserving the key patterns and relationships. This makes the data easier to visualize and analyze while retaining its most important features. Another fascinating application is image transformation. Operations like rotating, scaling, or skewing an image are powered by linear algebra, specifically through the use of matrices. For example, multiplying an image by the matrix r theta, known as the rotation matrix, results in the image being rotated. While technically it is the pixel coordinates of the image being multiplied by the matrix to determine their new positions, this simplified explanation helps convey the core idea. This process gives an intuitive sense of how linear algebra manipulates images in powerful and practical ways. It is a fundamental concept in fields like computer vision, where images are processed and transformed for tasks like object detection and recognition. Finally, linear algebra powers neural networks, one of the most transformative technologies in artificial intelligence. Neural networks rely on matrix operations to process data. Each connection in the network represents a weight, and these weights are organized in matrices. As the data moves through the network layers, these matrices transform the inputs into meaningful outputs. The diagram here illustrates a simple neural network with an input layer, a hidden layer, and an output layer. Linear algebra is the engine that drives these transformations, making tasks like image recognition, language translation, and recommendation systems possible. To summarize, linear algebra is the backbone of data science and AI. We discussed a few of its applications, such as simplifying complex datasets through dimensionality reduction techniques like PCA, powering neural networks, and enabling image transformation such as rotation, scaling, and skewing. Mastering these concepts will be a major milestone in your journey through data science, artificial intelligence, and beyond.